All right, guys, let's go over a few example problems from open channel flow. The first one will involve Manning's equation and uniform flow. We'll recall that uniform flow is kind of a theoretical thing that relates to when we have a continuous slope, a continuous prismatic channel, like a trapezoid or rectangle or a circular pipe. And that channel maintains a constant slope for a very long period of time or long distance. And the flow will eventually achieve a balance between the gravity-driven flow, so flow moving downhill, and then the friction along the boundary of that channel. And so when those two things are in balance, we get normal depth, and that could be supercritical or subcritical or critical. So our first example problem, this is a very typical kind of FE problem where we have a storm sewer. We need to convey a peak discharge of 10 CFS. This would come from a hydrologic model at 80% capacity. So that's like a typical kind of, the pipe can be up to 80% full. We don't want it to fill all the way up because then we run into pressurized flow and other problems. The slope is 1%. The material of the pipe is concrete. So what's the required diameter of the pipe to convey this design discharge? Assume N is constant with depth. So whenever you're just given a discharge and kind of an overall channel type of conveyance structure, we're going to go with Manning's equation. It's just kind of the default approach. So how to start this? Well, let's write out Manning's equation. So Q is equal to our Manning's constant all over N. And then because we're doing Q, we have to multiply it by area. Hydraulic radius to the 2/3, and then slope to the 1/2. And here, this is always the friction slope or energy slope, the slope of the energy grade line. But we typically assume that the bed slope is approximated by the energy slope. All right, so they gave us the Manning's roughness, and well, they gave us the material of the pipe. So let's look at what the Manning's roughness might be. So we go back to our book and look all the way back to chapter 3, Manning's equation, table 3.3. So with Manning's equation, because it's in the denominator, the bigger it is, the more rough we have, more rough channel we have, and the velocity or the discharge would decrease with a bigger Manning's N number. All right, so we want concrete precast pipe somewhere between 0.11 and 0.15. We'll just pick in the middle, 0.13. So we'll say N is equal to 0.013. Sometimes this is given in a problem. And then let's think about some other things. Well, area is going to be whatever the diameter of the pipe is. So d squared pi over 4, that's our area. That's at full, right? So if the pipe is full, then the cross-sectional area is going to be that. The cross-sectional area for a circular channel is complicated. It's in this table 6.1. We're not going to go there. So we're going to use a nomograph. So area full, hydraulic radius full is equal to d over 4. And remember that hydraulic radius is area over the wetted perimeter. And then our slope is 0.01. All right. Now to solve this problem, we're going to go to our nomograph. Okay. So the way this nomograph works is we start with the relative flow depth. So little d is the flow depth over the diameter of the pipe, big D. We said that we're going to be at 80% full. And so here's 0.8. Now we'll trace across, and there's a lot of lines here, so we got to keep them straight. Let's look at discharge, and we're going to say that n is constant with depth that was given in the problem. So the Manning's roughness doesn't change as the depth increases. So that means we're going to be on this dotted line right here. Okay, so that intersects our 0.8. And then we come down, oh, look at that, it's 1. Okay, so that's pretty convenient. So whatever the discharge is at 0.8 divided by discharge full is going to be 1. And so note that all these values over here are going to be whatever velocity, discharge area, or hydraulic radius that you have at whatever fraction of depth you have related to what those values would be at full. And so we know what hydraulic radius is at full, we know what area is at full, because those are easy to calculate from the circle formulas, but it's harder to calculate area at 0.8 or 0.7. Okay, so now we know that Q over QF is going to be 1, and that's just because we can actually go greater than 1 over Q over QF, and then once you get to full again, you've got that whole full wetted perimeter, and so there's more friction. So there's this actually maximum value at around 0.92 or something like that. Anyway, we'll go back to the problem. So Q over QF is equal to 1. Now we can go back to Manning's equation. We can say, okay, well, we know what area full is, and we know what hydraulic radius full is, because those are simple formulas from the circle. And Q over QF is 1, so we can say Q over QF is equal to 1, and so QF is equal to 10 CFS. All right. So let's go into our Manning's equation, and let's solve it in terms of diameter. So we'll do Km over N. Our area is pi over 4 d squared. Our hydraulic radius is d over 4 to the 2/3. And then we have our slope to the 1/2. All right, now let's continue and bring all of our diameters together, because ultimately we need to solve for diameter. So Q is equal to Km over N, pi over 4. We'll bring out our 4 to the 2/3. And then we'll have d squared and then d to the 2/3. So let's put everything in terms of thirds. So this would be d to the 6/3 times d to the 2/3 gives us d to the 8/3, s to the 1/2. And then we bring everything over and solve for d. So d ends up equaling Q on top, and we'll have 4 to the, this would be 3/3, so that'll be 4 to the 5/3. That's 4 to the 3/3, and then 4 to the 2/3. And then we'll have on the bottom Km, and then S to the 1/2. And then there's a pi in there as well. Okay, so now this was d to the 8/3. So cross that out and make this to 3/8. And then we can plug our numbers in and solve. Four to the 5/3. Remember, when you enter that in your calculator, you got to put it in parentheses. Pi, because we're dealing with CFS, Km is equal to 1.49. And then our slope is 0.01 to the 1/2. All to the 3/8. So this is a doozy to put in your calculator. Maybe you do this part first and then do the 3/8. So we end up equaling so we end up with D is 1.47 feet, or we can just call it 18 inches, 1.5 feet pipe diameter. So we round up to the nearest 6 inches typically. Now we have a storm sewer design that can convey 10 CFS at 80% capacity. If we had, say the problem said 60% capacity or something like that, well, we would just look up Q over QF. Here we're going to intersect this dashed line. We'd find what that ratio is, and then we would just multiply this by the design discharge, or sorry, take the design discharge and divide it by this so that we would get the QF, the Q full, solve Manning's equation using the Q full, and then solve for D. So ultimately we're solving for D, it's a funky equation. Another thing to note is that the units are inconsistent. With Manning's equation, it's an empirical equation, and then this Manning's N could have some funky units to make all the units work out, but we just kind of ignore units with Manning's equation because, again, it's empirical. It comes from data. It's not a unit consistent kind of equation. For the next problem, we'll talk about specific energy and critical depth. So say we're given a rectangular channel, flow is 1 meter deep. We're given a bottom width of 6.6 meters and a discharge, as well as a slope. Well, this is kind of setting up to be a Manning's equation type of problem because you're given slope and discharge. And this is actually from the homework where we had you calculate the bottom width. And the way to do that was to simply use the Manning's equation, solve for width. It ends up being a problem where you have to solve, you have B on both sides, and you can use Solver and Excel to figure out what the width is. Okay, well, for this problem, we're going to get to specific energy. So we're given these parameters. Let's calculate specific energy and Froude number, and then say, is this sub or supercritical flow? Okay, well, specific energy for rectangular channels is equal to y plus q squared over 2ga squared. Again, this is only for rectangular channels. Actually, that's not really true. This is for any channel because the area, as long as you know what the area is, the flow. Okay. So we can actually just plug these numbers in, and we have a flow depth of 1.0 meters. We have a discharge of 30 cubic meters per second, 2 times 9.81 meters per second squared times our area. And the area is going to be the depth times the width. So just draw this out. Here we go. So our area is going to be, and it's area squared. So we got to remember to square discharge and square the area. Okay, so E is going to end up equaling 2.06 meters. All right, now our Froude number is equal to V over the square root of GY. And this is just the definition of the Froude number. It's the velocity of the flow divided by the celerity of the gravity wave. So celerity is equal to GY for gravity wave. If we think about a wave moving in water, the speed of that wave, which is the celerity, is going to move at the square root of gravity times the height of that wave. In this case, we're dealing with the depth of water. That's what y is. So we want to see the ratio of the flow velocity to this wave velocity. So let's just plug in our numbers. Q over A is equal to V, and that's going to be 30 meters cubed per second, all over 6.6 meters squared. So velocity, well, we won't solve that out directly. So this is velocity, and then we'll put that all over the square root of 9.81 meters per second squared times the depth, 1.0 meters. So we can solve all of that, and it comes out to be 1.46. All right, so is it supercritical or subcritical? Well, it's going to be supercritical for fruit number greater than 1. We're going to be critical for fruit number equal to 1, and then we're going to be subcritical for fruit number less than 1. Because it's greater than 1, that means the velocity of the flow is greater than the celerity of this gravity wave. And so if you were to throw a rock in the river, it makes waves, gravity waves, and those waves would not be able to travel upstream because the water flow is going too fast. So it all gets washed downstream. So then we have supercritical flow. Now, the next kinds of questions or lead-on questions that we might have is to identify the alternate depth associated with this. So let's just take a look at the specific energy diagram, where we have energy on the x-axis and depth on the y-axis. We draw a one-to-one line where E is equal to Y. The specific energy curve looks something like this. So for fruit number, so for specific energy, in this case is, we said it was about 2 meters or 2.1 meters. 2.1 meters. Then our alternate depth, so this is the depth associated with that. This will be 1.0 meters. Our alternate depth is going to be at the same specific energy. So E is equal to 2.1 meters. What is that depth? Okay, so we'll just go back to the specific energy equation. E is equal to Y plus Q squared over 2G A squared. Or we could also write this as Y plus V squared over 2G. So we can calculate our velocity directly and plug that in. Well, in this case, we already solved for specific energy, so that's going to be 2.1 meters. That's equal to Y plus V squared. We'll do this one with the equation. So Q, all right, 2G, and then we know area of a rectangle is B times Y, right? The width times the depth squared. Okay, now we're going to have Y here and Y here. We're not going to be able to solve this directly. So maybe I wouldn't give you that question on a test, but we'll just go over how to solve it. So we need to solve for Y. We plug in the value for Q. We know our width. We know gravity. And so the way to solve this in Excel is to use solver. We would change our values of Y such that this side of the equation is equal to 2.1 meters. So you could just vary that by hand or use solver in Excel to do that. So Y ends up being 1.7 meters. So that's our alternate depth, Y2 we'll call that, 1.7 meters. We could also find our critical depth, and for rectangular channels, critical depth is equal to, should know this off the top of my head, but I want to make sure I get it right for you guys. Critical depth is going to be equal to there we go. So Q over B squared over G, and then all of that is to the 1/3. And this is for rectangular channels. So we could calculate our critical depth that way, plug in the bottom width, the discharge, gravity, and we get our critical depth. And that's what this value would be right here, where we have our minimum specific energy. Another thing to note about the specific energy diagram, it's definitely something I want you guys to be able to work with and interpret for the exam, is, so here's our curve, our specific energy curve here plotted out for that problem, those two alternate depths identified at that given specific energy. Really close to critical depth, you'll notice. One thing else to notice is that this blue curve, which is our specific energy curve, it eventually approaches the one-to-one line between specific energy and depth. And the idea is, as your depth increases, the velocity decreases, such that your velocity head becomes negligible and the total specific energy converges to be just the depth. So whatever the depth is ends up dominating the specific energy of the equation. As you go down here, the velocity is increasing very much. You can see that the depth, for a tiny decrease in depth, you get a big decrease, or big increase in specific energy. That means the velocity is increasing very quickly. Okay, another problem we'll look at from the homework is choking and how to kind of calculate choke-related problems. So the way I set this up is we're dealing with the same rectangular channel you had before. We need to install a weir that will just induce critical depth, or just cause the water to choke, but not quite. What height should this weir have relative to the bed to induce critical depth at the weir? So let's just draw this out, and we'll draw it as flat here. So here's our channel. We've got flow coming in, and then we'll just draw this weir like this. And so the flow is going to come down and hit critical depth, and then maybe it'll go back up or something like that. All right. So up here we have y1 is equal to 1.0 meters, which is given. We've got our discharge coming in at 30 cubic meters per second. And we ultimately want to calculate this delta Z value. And then this we'll call YC is equal to Y2. So this will be 0.2, this will be 0.1. Okay, so the first step here is when we're dealing with rapidly varied flow. So this is a rapidly varied flow situation. And we're going to assume that there's no energy lost here. Maybe that's going to be something stated in the problem. Between points 1 and 2. Okay, so let's write out our specific energy equation. E1 is going to be equal to E2 plus delta Z. This is the kicker here. This is kind of the crux of the problem. Whatever the specific energy is here, well, it's not going to equal to the specific energy at critical depth, because we know that's the minimum specific energy. We're not at critical depth here. Or actually, it's super critical. Anyway, so in order for these two to be equal, well, we have to account for delta Z. So critical depth is going to be the minimum energy. Delta Z is going to offset that so that these two are going to be equal to each other. All right, so then we can calculate delta Z is equal to E1 minus E2. All right. And then we'll remember that E2 is going to be equal to EC. So E2 plus delta Z is equal to E1. All right. Now for rectangular channels, this is just by definition, EC is equal to 3/2 YC. Okay, that's good. But we have to calculate YC, and YC is equal to little q squared over G to the 1/3. Little q is called the unit discharge. That's discharge over the bottom width of the channel. Bottom width of the channel, flow depth. Okay, so now we can calculate from the discharge in the bottom of the channel, we can calculate our critical depth, and then we can calculate our critical energy, which is also equal to our energy at point 2 in the flow. And then energy at point 1 in the flow is just the specific energy equation from before. So delta Z is going to be equal to E1, and E1 is going to be V1 squared over 2G plus Y1, and then E2 is going to be our critical depth. So that's going to be 3/2 times YC, and then we'll plug in this thing for YC. So Q, little q squared over G to the 1/3. So that's our YC. Okay, now we just have to solve this. There's a lot of things to plug in here. So V1 is going to be equal to 30 cubic meters per second divided by area, which is 6.6 meters squared. Remember, B is equal to 6.6 meters. And then our flow depth is 1 meter. So that gives us 4.56 meters per second. All right, little q, 30 cubic meters per second divided by 6.6 meters is the bottom width, and that gives us 4.56, whoa, shocker, meters squared per second. So those are the units of our unit discharge, the discharge per unit width. So every meter has this value of meters squared per second. And then we just plug everything into delta Z. So our velocity, 4.56 meters per second, squared over 2 times 9.81 meters squared per second, plus our flow depth, 1.0 meters, plus 3/2 times little q, 4.56 meters squared per second, divided by gravity to the 1/3. All right. Sorry, this should be minus. If we go back, we're subtracting E2 out. We end up with delta Z is equal to 0.13 meters. So this is the rise in elevation that we need in the bed to result in critical depth of the flow. So this would just cause choke. Anything above this would actually choke the flow, and you would end up with a greater depth upstream. Last problem I'll go over for this homework is a hydraulic radius question. And we're given a triangular channel, the 1-to-1 side slope, and a flow depth. So anytime we have a hydraulic radius question with a non-rectangular channel, we've got to go to this table right here and take a look, because things can get a little funky when we diverge from rectangles. So the hydraulic radius equation is just right here. M is going to be the side slope. If we have a 1-to-1 side slope, that's vertical to horizontal or horizontal to vertical. Sorry. So if it were 2-to-1, M would equal to 2. If it were 3-to-1, M would equal to 3. Here we're given M is 1, so 1-to-1. So we plug 1 in here for M, Y is our flow depth, and then we just solve this equation. So let's do that. Hydraulic radius, sorry, we say M is equal to 1, Y is equal to 5 meters. Our hydraulic radius is equal to M, Y over 2 square root of 1 plus M squared. All right, now you could solve this yourself based on the side slope or based on angle. It doesn't matter, it's just the formula for area of a triangle over the perimeter of a triangle. R is equal to area over perimeter. Okay, so let's just plug our numbers in. 1 times 5 meters all over 2 square root of 1 plus 5 meters squared. All right, and that's going to end up equaling sorry, M is 1. So this is going to equal to 5 meters all over 2 square root of 2, which is equal to 1.77 meters. That's our hydraulic radius. Now, if I said do this for a trapezoidal channel, the 1-to-1 side slope, we go back to our table here. Here's the formula for the hydraulic radius. You'll notice that it's just the area over the wetted perimeter. And in this case, we need the bottom width as well. So that would be B, M, and Y. So just plug all these numbers in, calculate our hydraulic radius. It's a common FE type of question. If I had a circular conduit type of question, let's go back to my trusty old nomograph. Say I had a diameter that was given, and I had a flow depth. So the diameter, say the diameter is, we'll just do that for a circular channel. So circular conduit at 60% flow depth. Find hydraulic radius. Well, 60% flow depth, and hydraulic radius is our curve over here. So we'll go all the way out here, and then we'll come down, and it says our hydraulic radius is going to be about 1.1. We'll just go to that. 1.1 of the hydraulic radius at hydraulic radius of full. So R over RF is equal to 1.1. For a circle, the hydraulic radius is going to be D over 4. You can prove that to yourself. So we would just do 1.1 times D over 4. And they would have to give us a diameter for this problem in order to calculate this. So say diameter is equal to, we'll say 18 inches or 1.5 feet. Then we'll just do 1.1 times 1.5 feet over 4. So whatever that ends up equaling. So that ends up being our hydraulic radius. And note that it has units of length.